Hello there everyone. It has been a while since I posted a video lessons. What we are going to do today? Um, Today we are going to learn or discuss root finding method. So you have learned to use factorization method and using formula to do this before, especially with quadratic equation and cubic equation. So what is root? Okay, so a root to an equation is a value of the variable that involved in that equation, such that when you substitute that value into the equation, it will satisfy it. So it means that whatever you have on the left hand side will be equally equal to the value on the right hand side. So for example, let's say we have equation 15 equals to x square plus 2x. Okay, so this is an equation with the variable x. So if a value of x, when you substitute into this equation, it will be equal to 15 on the left hand side, then that value of x is the root. For example, if we put x equals to 3, okay, you can see that the equation will satisfy because 3 square plus 2 times 3 will again equals to 15. So x equals to 3 is called a root. On the other hand, for example, if I substitute x equals to 2, for example, x equals to 2, so you will see that again, this one will not be the root, because when you substitute this value x equals to 2, what you have is 8. So it's not the same. So x equals to 2 is not the root. Okay. So, but however, normally and traditionally in school, you might understand the root such that it is the value of x, such that um, it will make the equation of x square plus 2x minus 15 equal to 0. So normally student would see if it is equal to 0, then you call it a root. And if it's not equal to 0, then you might not say, oh, you might say it is not a root, and so on and so forth. But that's traditionally and normally in school, you might say, or you might know root when you see that that value of x, when you substitute inside the equation, is equal to 0. So, well, of course, it's still the same because we just rearrange that. We rearrange the equation into this equation. So it is a similar equation. It's just we rearrange that. So still, x equals to 3 is the roots of the equation, because if you substitute into this equation, you will still get it equals to 0. Okay, under this numerical method chapter, the question is why we need numerical method. So, well, life is not that easy, is it? So some of you might say that it is too obvious that for equation x square plus 2x minus 15 equal to 0, x equals to 3 is the root. But what if we change the coefficient of this equation a little bit and see whether it's obvious or not. For example, if I change this equation into x square plus 0.2x minus 1.5 equal to 0. So now by using factorization, it's not that too obvious, and you might find it difficult to do factorization here. And also you might use formula, still be able to do it, but well, we're just not dealing with a quadratic equation in the real life. You might have encountered a much more complex equations, which is the b square minus 4ac, for example, the determinant and the formula of b negative b plus minus b square minus 4ac over 2a, it doesn't work anymore, especially when you go to a higher degree of equation and so on. So based on this equation, take a guess, what is the root? Okay, what is the root? So you might ask, can I just make a just substitution into this equation and then find the value of x, so that when I substitute again and again, I will get it into to 0? Well, I'm going to leave that to you to answer by telling you one of the root is 1.1288205 72745. So if you look at the root and you try to like successfully guessing, I'm not sure how long it's going to take to get this. So happy guessing. Okay, so again, the equation can be quite complex that we will need another method to find it. So before we move on, so what is numerical method? Okay, so numerical method is a method that give an approximate value. In this case, the root up to a certain desired accuracy. So if you look at the root that I just wrote down just now, it consists of so many decimal points. So that is what we call the accuracy. Okay, so sometimes we just want to know the first two decimal points and so on and so forth. Alright, so the first numerical method that we're going to learn in the root finding is called iteration method. So let's consider the equation of x squared plus 0.2x minus 1.5 equal to 0 again. Okay, so there are a few things that we need to consider first if we want to use the iteration method. So first of all, we need to locate roughly the position of the root. How? So what we do, we pick an interval. Well, maybe in exam they will give or they will specify the interval, and you just need to show there is a root lies inside it. So we might not need to waste time looking for the root in which there is not in there in the first place. So in this lesson, I would like to check whether the root lies in the interval of, let's say, 0 and 2, okay, including 0 up to including 2. So to start with this testing, let's first define fx equals to x squared plus 0.2x minus 1.5. So what we do first, for when x equals to 0, we substitute this 0 inside this function. So you can see that you have negative 1.5. Okay, so when you substitute x equals to 2, so what you have is 2 square plus 0.2 times 2 minus 1.5. That will give you how much is it? 2.9. Yeah, 2.9. So as you can see here, because the value of fx at the end of the interval change the sign, it means that there is a value of x somehow in that particular interval that when you substitute, it will pass or make it 0. So as again, if the value of x that you substitute inside the function and return you 0, then you know that the value is a root. Okay. All right. So that is how you check whether there's a root lying in the particular interval or not. So you just substitute the end point of the interval into the function. Then you check whether there's a change of sign. It not be necessarily be a negative first and then positive. It could be positive to negative also. So next, what we do after we know that there's a root lying in that particular interval. So in order to do the iteration method or to use iteration methods, so we have to find what we call a relation such that, okay, so I'm going to write down first the relation such that xn plus 1 equals to a function f. This is a capital F, okay, capital F, x, so capital F is a function of xn. So why we have to do this? Because we don't want to do the blunt guessing on the roots and so on, because in this particular relation, if we be able to write down in this relation, hopefully by certain condition, it will automatically bring you to the roots itself, converge to the root itself. Okay, so don't bother about the subscript for now, n plus 1 and xn. What is this is saying is that the next guess of the root will be much more better or depends on the current guess. So this could be go away from the root also, or it can say it diverge also, or if you are lucky enough, then it will go to the root itself. So we'll talk about this more afterwards. Okay. All right. So so by using the relation that I have written here, we are going to do this successively until the left hand side is almost, or we can say close enough to each other. Okay, so that means the equality itself have been achieved. So if we be able to do that, that means that we already find the value of x, which is the root to the equation. So the point is, how do we get this relation from our current equation? So let's consider again, or write back the equation we have, which is x squared plus 0.2x minus 1.5 equal to 0. All right. So one way we can do this is, let's try to bring this one equals to 1.5 minus 0.2x. Then x, we take the square root. Okay, square root of 1.5 minus 0.2x. Okay. All right. So now if we compare this form, okay, to this form, okay, I can say that now I say the form looks similar in a sense that if I just say this is xn plus 1 and this is technically the f xn, so I can write this as xn plus 1 square root of 1.5 minus 0.2xn. Okay, so this is one relation that we have from the equation itself. So how else can we form the relation? So other than that, we can also say What if I put this one as 1.5 minus x square? Then I can bring this down, x square over 0.2. Again, I can write this as xn plus 1 equals to 1.5 minus xn square 0.2. Okay, is there any more? Maybe we can also um, um, okay, so we can also put x square equals to 1.5 minus 0.2x. Then we divide both sides by x, so we left with 1.5 over x minus 0.2, and we can write this as xn plus 1 equals to 1.5 over xn minus 0.2. So in this case, your fxn is equals to 1.5 xn minus 0.2, and for this one, xn is equals to 1.5 minus xn square over 0.2. All right, but so far we established three relations, but for the time being, I have to say that all of these three relation might not all of it converge to the root that we try to find, because of certain things that we will be looking later. Okay, so why now we are going to look into why out of these three maybe one or maybe two can work, but how are we going to see whether in the first place why you need this relation? I'm going to discuss this in this approach in a way that, okay, so let's say I consider all of these three. So what I have done, for example, if I say that because, for example, x equals to 1.5 minus 0.2x, right? So I can say that this is let me, okay, so write down first. So x equals to 1.5 x square over 0.2, and also x equals to 1.5 over x minus 0.2. So you can see that we have the same x on the left, so I'm going to say that each of these will be written as gx equals to x. Okay, so the left hand side. All right, so now so this one, okay, I'm going to label this as fx. Okay, so again, this is also another fx, and this is also another fx. If you want, you can say 1, 2, and 3. All right, so for each of these case, what I'm going to do, I'm going to plot. Okay, let's see, we plot this relation, okay, the first relation, the second relation, and the fourth, and so on, together with the original function. So let's see why this thing can works, and how you know that the value that you come out with from this relation is actually the root. So let's see to the graph. I have pre-prepared this graph. So if you look at this line, there are so many graphs here. So this is the original graph for, okay, so let's say this is fx equals to x square plus 0.2x minus 1.5, this particular purple one. All right, then this one is the gx equals to x. So, and this one is the square root of 1.5 1.5, what is it, minus 0.2x. Okay, and this one here is 1.5 over x minus 0.2, and this one is 1.5 minus x squared over 0.2. So remember the first relation we have is gx equivalent to gx here is actually x, okay, equals to square root 1.5 0.2x. So where is that line? So as you know, when you have equality here, so you can see that g, this line and this line actually meet at this point, right? And this point is actually, if you see the red dotted line, is actually cutting to this point, which is actually the root of the original equation. So that's why based on this equation, the relation, you can see that if we can determine the left hand side equals to the right hand side, it will immediately show that it is the same as the root. And we can consider the other relation also, like the gx here and the quadratic here. You can see that all of them are intersecting at the same particular point, which is exactly having the same, defined by the same value of alpha, x equals to alpha here. All right, so that's why this relation works. Okay, so but not all of them will, when we do the iteration later, will converge to this point. So let's see one by one. Okay, so let's consider the first one. So this one looks like a straight line, but actually it's not a straight line, because it looks like a straight line because I have zoomed in into that particular interval 0, 1 and 2 only. If you increase the interval, you can see it's going to have this kind of shape. Okay, so let's have a look here. So this is the line of our square root, and this is the x itself. So because we have checked that in this particular interval, by the change sign of the function, there is a root. Of course there is a root. Now you can see there is a root over there, but for now we don't know what is the value of it. So let's say to do the iteration, we have to pick a guess in that particular interval, because we know it's there. So if you are lucky enough, it will be faster converge to the point or not. So let's see, let's pick, for example, I pick let's say we pick 1 here. Okay, so if we pick this particular value 1 as our starting point, you can say x0 equals to 1. Okay, so now first bring, you can see if I put a dotted line here up to this point, right? And this point here is referring to the point of, this is a function this point, right? All right, now from this point we have to go left or right, as long as it can go into the x line, so this line. So we go to the right, so we reach over there. And if we bring this down, okay, you can see that this is another point x1, and from that particular point we go back to the square root function equation, then we move it to the side and reaching the x again, then you can see that now this is x2, and from this x2 we go to the square root function again and you go to the left, to the right again, then eventually it will go to this point. So this is the illustration of how now you can see that. That's why if I say that you can see that x1 is depend on the value of 1.5 minus 0.2 times x naught, right? Because this value, this part is actually this value, and this value on this line is x1. Okay, x1. So that is for the first relation. So now let's consider the second relation we have. This is, I think, 1 over 5 over x minus 0.2, and this is x. So let's start at 1 again. So if you start at 1 in this case, so first we go to the green line, you go to the green line, then you go to the right, because that is where you can see that the line will meet the x line. If you go to the left, you won't meet the blue line, so you won't meet here. So you go to this side. So when you go to this side, then you go down, then you know this is going to be your x1, this is x0, right? And you, after you go to the x line, you go to the green line again. So after going to the green line, so you go to the left because you want to meet the blue line as x, and you can see that now this is x2. So if you go back, you go up to the green line, then you go to across, then you go. So you can see that for next value of x from x0, which is closer to the red dotted line, suddenly you go to x1, which is a little bit farther, then you go to the x2, which is even further away from that, and eventually even further and further. So that's why you know that based on this diagram, you know that this relation will not converge to the root itself, so it's in fact it's going to diverge. All right, so how about the third one? So the third one, let's say we start at 1 again. So first we need to go to the pink color, the pink. So you go to the right. So I'm not sure whether it's going to touch it here or not. So eventually it might touch it on this far side. So you go down. So obviously if it touch it somewhere here, so you want to go to the so if we extend this, so maybe here, so you have to go, you cannot go up because there's no purple line up there, so you have to go down. So you go down, maybe it will eventually reach somewhere here, then from that you have to go left, because you can see the blue line is slanting towards this side. So but eventually you will go, and you can see that obviously the value of x is getting further away and further away on the left and the right hand side, and eventually diverge. All right, so it's not going to converge. All right, so you can see that the all of this relation, how it will converge or not. All right, but then the point is, if we have the equation which is quite complex in the future, which is we might not have idea how the graph it looks like, it's kind of like very difficult for us to use this particular graphical method to determine. So what we do based on our textbook, so we're going to use the relation of u. So let's consider this equation again. 1.5 minus 0.2x. So okay, so let's write this as 1.5 minus 0.2x of 1/2, and you have to remember that this is actually your fx. Okay, so we just ignore the subscript here, because the subscript is meant for the iteration process, but the equation, it will be still stay as usual, right? So what we do, we going to make use of this uh, inequality. So you, other than using the graphical, you can check this. Okay, what if the first derivative of the function on the right of the relation, and you put a value here, let's say alpha, and that alpha is in the interval, where in our case is 0 and 2 just now, so somewhere in the middle there. So you know that this particular function on the right will converge. So let's try to do this for this one. So let's say now fx equals to 1.5 minus 0.2 x half. So we differentiate that once, so we have 1/2. So I hope you know how to do differentiation here. So you have 1/2 and also negative 0.2. Right. So if we pick a value, so just now we pick 1, right? And of course we still don't know whether 1 is a root or not, but as long as it is in the interval. So if you substitute, for example, 1 inside here, or where is it, 1. Okay, so let's substitute 1. If you substitute 1.5, we have minus 0.2, you have 1/2, and you calculate this as 0.2. You will see that this value, hold on, let me find a calculator and do this calculation. So you have so you have this equals to negative 0.0877. Okay, so if you repeat the same procedure for the other two relation, so it is 1/5/x minus 0.2. So if you differentiate this, so you have negative 1.5 x square. So if you substitute 1 just now, you get 15. So which is, it is not inside this interval. Alright, so it's outside the interval, so that's why we can see from the diagram it's also diverges. So I believe if you also try for the other one, I think 0.2, you will check that this value also will be bigger than, or bigger or smaller than, it's not in the range, it's not in the range. Okay, not in the range of this one. Okay, so you might want to check that by yourself. All right, so we have seen why the relation work and some cannot work. So let's go to the example of the question in the exam, maybe. Okay, so for example, I have typed this out for you. So where is it? Okay, so this example 1, for example, I'm using the same example, I type it more properly now. So show that the equation of that has at least a real roots in the interval. So again, I've shown you just now, so you might want to go back to the video just now. So you should be able to answer this one. Okay, determine which iteration of that, this one or this one or this one is more likely to give a convergent sequence of approximation in that particular interval. So now this one, you might want to use the things that we have discussed just now. So check this value. Okay, if it is lie in between this particular value, then you know that that particular relation will um, converge to the roots, right? In this case, we only asking for the roots on in this particular interval because it's quadratic. You can see that there's another root in the negative side, so which is lies in the different intervals. So you, if you want to find that root also, yeah, you can you have to check this particular condition again, whether it is which one is converging and not. So in this case we want to use this one, so I'm going to show you this one. So we have seen that this particular n plus 1 equals to 1.5 minus 0.2 xn will give you a convergence sequence that will bring or give you the approximate of the roots. So let's start. So now let's x naught equals to 0.5 here, okay, here. So if x naught equals to, so the next value x is, now this is saying that n is equals to 0. So when n equals to 0, so you have 1 here, so equals to 1.5 minus 0.2 x0, which is, this one is actually 0.5. If you calculate that, you will get 1 point, what is it, 1.1832. So this is x1 now. So okay, when we do the iterations, you do the iteration until the value has seems to be converging to one particular value. So by doing the first iteration, we still don't know whether it's a root or not. So let's continue with x2. You substitute this value x1 here. So because we looking at the three decimal place, I'm trying to keep it as 4 first, as in the working. So if you, okay, calculate this one for a while. So you will get 1.124. So you can see that between these two value, the changes is still significant. So you continue for s3, 1.5 minus 0.2, then 1.1240. Okay, let me calculate again. Alright, so the value is 1.1292. Now the difference is less now, but still we want to check again. So you repeat this, okay, and 2. So we get what, sorry, 1.1288. Alright, so x power x5 will be 1.5 minus 0.2, 1.1292. Sorry, so we have to substitute 1.1288. okay, so because we are keeping up to 4, so okay, so now it looks like there's no more changes, because if you continue with the x6, you just substitute this value inside, so you get back 1.1288. So what is the root that I gave you just now? It is, okay, so you can see that here, okay, so because we want 3 decimal place, so x is approximately 1.129 is the root of the equation. So one of the root. So another root would be, I don't know, maybe it's a negative something, so I'm not sure. So you have to check back using your calculator for this particular example one. All right, so I hope by showing you this, at least you can go and try out some of the exercise in our textbook. And so I hope you can see this video again, just to give you a little bit of understanding of what is going on in this numerical method. And see you again in the next complementary video lesson. So make sure you have done your exercises, so I think it will be good for you and for your exams later. All right, so that's it from me.